Alright, so we're ready to start chapter 6, which is modeling random events, the normal and binomial models, right? So this is a pretty short chapter. There's only 3 sections. Right? So some chapter 6 topics we want to look at is we want to be able to distinguish between discrete and continuous random variables. So we're going to go through that with some examples. Be able to apply a normal model to find probabilities, and be able to apply a binomial model to find probabilities. So 6.1 is titled Probability Distributions, right? So in this, we're going to look at what is a probability distribution. We want to be able to distinguish between discrete and continuous random variables, and be able to use probability distributions to compute probabilities. Right? So a probability distribution is a table or a graph that tells us these two things. One, all the possible outcomes of a random experiment, and 2, the probability of each outcome. Right? And a probability distribution is often called a probability distribution function or a PDF. Right? So probability distribution. So we can display a probability distribution using a table or a graph. So here's one example of using a table. So the experiment that we're doing is rolling a die. So notice on the left we have X, so these are listing all the possible outcomes, right? We can have 1, 2, 3, 4, 5, 6. And then on the right, we get the probabilities listed, right? So the question asks, what's the probability of rolling a 5 or a 6, right? So rolling a probability of a 5 or a 6, we would add these probabilities together, right? 1 6 plus 1 6 get 2 6, which is 1/3. Right? So if you want me to draw that out for you. Hook up my pen. Right? So the probability of getting a 5 or a 6, right, is the probability of getting a 5 plus the probability of getting a 6. So this would be 1 6 plus 1 6 equals 2 6, which is 1/3. Right? So these are mutually exclusive, so we don't have to worry about subtracting their intersection, right? Because the intersection would be 0. You can't get a 5 and a 6 simultaneously if you're rolling a die one time, right? So the next slide I have is looking at a graph, probability distribution graph. So it asks us to estimate the probability that a randomly selected reviewer gave this book a 3-star rating, right? So we would want to come up here and follow the 3 across, right, to estimate. So it's really close to 0.1, right? So maybe if you had like a ruler with the graph, it might be easier to know for sure, right? But just drawing that by hand, it looks really close to 0.1, right? So we could just estimate that the probability is 0.1, right? So here with the graph, notice that we have down here we have what we're considering, right? And then along the y-axis is the actual probability. All right. So another thing that we want to talk about in this section are the difference between discrete and continuous. So we have 2 types of numerical variables. So discrete is things that we can list or count, right? So some examples are the number of siblings that you have, the number of songs on an MP3 player, right? In other words, when I ask you how many of these do you have, you always answer in the natural numbers, right? 1, 2, 3, 4, 5, and so forth. right? Where if something is continuous, we can't necessarily list or count them all because they occur over a range of values, right? So example is height of a basketball player, right? So someone can be 6 foot 3 inches or 6 foot 3.6 inches, right? It's not just 5 foot or 6 foot or 7 foot, right? There's a whole range. Same with like a weight of a sandwich, right? The sandwich could be similar in that fashion. All right, so let's look at some examples of discrete and continuous. So here we want to label each of the variables as discrete or continuous. So 1 is the number of cars owned by a household, right? So if I asked you how many cars that you have, right, this is something you're counting, right? So this is discrete, right? Number 2, number of pets owned by a student, right? This would also be discrete. Right, we can't have like 2.5 cats or whatnot, right? Number 3, time it takes a worker to commute to a job site, right? So this would be an example of continuous, right? And 4 is also continuous, right? Height of a building in downtown San Francisco, right? So in other words, again, one easy way to know is discrete, the only options are in here, right? So like if I ask you, well, we could also include 0, right? So like number of pets owned by students. So you either have 0, 1, 2, 3, 4, 5 pets. We have nothing in between, right? Same with number of cars, right? So this is discrete. And if my options are in between these values, then that would have to be continuous, right? So on the next slide, I have those solutions just typed up for you, right? So we have 2 features of probability distribution, right? And these are items that we've talked about before, but make sense, right? Remember that all p of x values, all my probabilities have to be between 0 and 1, and that's inclusive of 0 and 1, right? So p of x has to be in between 0 and 1, right? And the sum of all p of x values must equal 1, right? So the sum of p of x, all my p of x values have to be equal to 1, right? So in other words, if I add up all the possible outcomes, all the probabilities, that needs to add up to 100%, right? Because there's a 100% chance that one of those will happen, right? So those are two key features. If those 2 things are not true, then it's not a probability distribution, right? So the next example we're looking at is creating a probability distribution. So this is an example that we have, and we want to make our own probability distribution. So if we roll a fair 6-sided die, right? That's the experiment we're doing. We can win $10 if you roll a 5 or a 6. You lose $5 if you roll a 1. For any other outcome, you win or lose nothing. So we want to create a table showing the probability distribution for the amount of money you win playing this game, right? So here I have listed. So there are 3 possible outcomes, right? We either win 10, lose 5, or win, lose nothing, right? So I have that shown here, right? So these are my possibilities for x, right? So positive 10 means we gain $10, negative 5 means we lose $5, and 0 means we're not winning or losing nothing, right? So the probability of rolling a 5 or a 6 and winning $10 is 2 out of 6, right? So how we got that, right? So the probability of getting a 5 or a 6, right, is the probability of getting a 5 plus the probability of getting a 6. So this would be 1/6 plus 1/6, we get 2/6, right? Or you could reduce that down to be a third. So the probability of rolling a 1, right, is 1 out of 6, right? And note that means we're losing 5. So then if we win or lose nothing by getting a 2, 3, or 4, the probability is 3 out of 6, right? So the probability of getting a 2 or a 3 or a 4, right, is the probability of getting a 2 plus the probability of getting a 3 plus the probability of getting a 4, right? So we have 1, 6 plus 1, 6 plus 1, 6, right, because it's a fair die. That gives me 3 out of 6, right? So on the next slide, I have the table shown here, right? So these are my x's, these are my p of x, right? So we made our own probability distribution. And you might be wondering why we're not showing 1 through 6 on the die, right? Well, those aren't the outcomes, right? The outcomes are if we're winning or losing money, right? So we used the die and numbers 1 through 6 in order to get the probabilities, right? So the probability of losing $5 is 1 out of 6, right? The probability of winning or losing nothing is 3 out of 6, and the probability of winning $10 is 2 out of 6, right? So note that all of my p of x values, all of these are between 0 and 1, right, which is good. And the sum of all the p of x values are 1, right? 1/6 plus 3/6 plus 2/6 is 6/6, right, or 1. So all these added up give me 1, and they're all in between 0 and 1. So thus we have a probability distribution. Right? So next, looking at probability distributions for continuous random variables, right? So it's not possible to list all outcomes for a continuous random variable. So we cannot represent the probability distribution using a table, right? You could do it other ways, like with a function, but we're not going to get in that quite yet. So our other alternative would be to use it as a fraction, or not a fraction, excuse me, a graph, right? So here, graphs called probability density curves we can use instead, right? So here's an example of a probability density curve. So here it says this probability density curve shows the probability of wait times before service at a coffee shop. The shaded area represents the probability of a wait time between 0 and 2 minutes. The total area under the curve is 1, right? So a probability density curve, if we know in between what values that we want to look at, the area in between those values of the curve is the probability, right? So that's why the probability under the whole curve has to be 1, right? Because that's the probability of getting something, one of the outcomes is 100%. So this area, right? So all this area, so this area is equal to the probability of getting in between a 0 and a 2, right? So probability of wait time between 0 and 2 minutes. So if I knew what this area was, I would know what the probability is to be in between these two values, right? So we're going to explore this idea more in this section, right? But for now, it's important to understand that if I knew the area under the curve, then I would know the probability, right? The area is equal to the probability. And to find this, we can use integral calculus to find that, which, you know, it's not expected that you've had calculus before this class. So I'm going to show you, we're going to use use the computer to find the area under the curve for us, right? So we can use R, we can use our graphing calculator to do this. So if we're trying to find a probability with a uniform distribution, so when we have more of this rectangle, that's easier done by hand, right? So it says a bus arrives at a certain stop every 12 minutes. The graph shows the probability distribution for wait times before the bus arrives. Use the distribution to find the probability of a wait time between 4 and 10 minutes, right? So over here, we have this uniform distribution, and they're all equal to 0.08333, right? You can see that here. Oops. See that here, right? So these are all uniform to this. So if I want to find the probability of wait time between 4 and 10, right? So I would have to come over here to 4, and in between 10. What I'm after is, what is this area? Well, this is just a rectangle, right? If I pull this apart, the width of the rectangle would be 6, right? And the height of the rectangle would be this y value, 0.08, and there's what? 1, 2, 3 threes. So how do you find area of a rectangle, right? We take length times width, right? So if I multiply those two together, I can get the area. So I have this more drawn out on the next slide, right? So this is the area I was looking for in the red, right? So the area is length times width. So we can take the width, right, which would be 6, right? We're going from 4 to 10, so that's where I get the 6 from. And then the height is the 0.08 number. So this gives me approximately a 0.5, right, or probability, right? So you'll do an example of this in your homework, right? So make sure that make sure you remember when you have a uniform distribution and we have like a rectangle, we can find that area, right, by doing something similar. Something else that you're going to have to remember to do in your homework. So I reminded you already, if we have probability of A or B, and our probabilities are and our probabilities are mutually exclusive, right? Remember that the probability is just equal to the probability of A plus the probability of B, right? So that's if they're mutually exclusive, right? Mutually exclusive, right? And if we have two events that are independent of one another, right, then the probability of A or B is equal to the probability of A times the probability of B, right? So you're going to need this fact in your homework also, right? So that will help you in the homework as well, right? So don't forget that from we looked at that in chapter 5. So then my last slide, so I kind of already mentioned this. So in general, right, when we're trying to find area under the curves, it's very difficult. So typically we're going to use some type of computer-based technology to find that, right? Alternatively, we could use integral calculus, as I said, but we're going to use technology in this class, right? All right, so that's all I have for this video. If you have questions over 6.1, please email me. Thanks.